Hey everyone, welcome back and let's write some more neat code today. So today let's solve Coco eating bananas. But before we do, I just want to say that if you do have any requested problems, you can feel free to leave those in the comments. I do have a large backlog of requested problems that I'm working through, so it may take some time for me to get there, but you can feel free to request at any time. And if you find this video helpful, don't forget to leave a like and subscribe for more videos. So this is a pretty interesting problem because there is a brute force solution that we can arrive at, and that brute force solution can easily be transitioned into a binary search solution, which is the optimal solution for this problem. So we're going to be working our way from the brute force to that binary search solution. So Coco loves eating bananas, and we have n piles of bananas given to us in a piles input array. We're also given a second parameter, h, which is the number of hours that we have in order to eat all of the bananas. So we have to eat them within h hours. And so Coco has a certain eating speed where she can eat a certain number of bananas. Still had inch more. That's why they get in this entire pile, because she could only eat 4 piles because we only have 4 hours, right? Coco can only eat 1 pile per hour. So if she ate all 4 piles over here, we'd still have 1 left over. That's why they guarantee us that h is always going to be greater than or equal to the number of piles. So the minimum in this problem, given this input array, h, the minimum it could possibly be is going to be 5. And I sort of wrote over it, but the last important thing that they tell us in the problem is we want to determine that eating speed k that Coco is going to eat at, but we want to know the minimum integer k, the minimum eating speed of Coco, that she could eat all of the piles in exactly 5 hours, or exactly whatever that time interval, that number of hours happens to be. So let's take a look at this example. They give us an input array of 4 piles, and they give us 8 hours to eat all 4 of those piles. What's the minimum k, the minimum eating speed that Coco could use to eat all of these piles in at most 8 hours? So we have to eat all the piles in 8 hours or less. Well, the brute force would be to start at 1, right? Because Coco could try k equals 1, right? Can we eat all piles in 8 hours then? Well, it will take us 3 hours to eat the first pile, right? 3 divided by 1, which is our k, right? 3 divided by 1 is going to be 3 hours to eat this first pile. And to eat the second pile is going to be even more. That's going to be 6 hours, right? 6 divided by 1, 6 hours. So far we already have 9 hours, and we haven't even eaten the entire number of piles. So therefore, k equals 1 is not going to work. And we could just continue this brute force approach, right? Now try k equals 2, right? And then do the exact same computation with k equals 2. Now, my question to you is, we know that the minimum possible solution would be k equals 1, right? K can't be 0 because that would mean we're not eating any piles. So the minimum is 1. What's the maximum that k could possibly be given this input array and given this number of hours? Well, remember, the number of hours is always going to be greater than or equal to the number of piles. So in the worst case, k would basically be the max number that happens to be in our piles. For example, if k equals 11, right? That means we're able to eat the max pile in exactly 1 hour, right? And if we can eat the max pile in 1 hour, that means every other pile is also going to take us only 1 hour. So therefore, we're going to eat every single pile in 4 hours. And we know for sure that this is going to be less than whatever is given to us as h, right? We guaranteed that at the beginning. So really what we're doing here is we're going to try every single value from 1 all the way up to 11, which happens to be the max value of our piles. And the first value that we get that allows us to eat every single pile in less than or equal to 8 hours is going to be our output. So we're going to end up trying 1, we're going to end up trying 2, we're going to end up trying 3, and we're going to find that 4 allows us to eat all the piles in less than or equal to 8 hours. So this is not a terrible solution, right? Even though we're brute forcing the entire solution set, 1 through the max of piles, it's not going to be terrible. What's going to be the complexity of that? Well, we're potentially going to have to iterate through every value in this potential solution set. What's that going to be? Well, 1 through the max value of our piles, right? So it's going to be, let's say, big O of the max value of piles, so max of p, multiplied by the length of p, because for every k value, we're potentially going to have to try, okay, if I eat all these, how many hours is that going to take me, right? So we're going to have to iterate through this entire array for every k value that we try. So we're going to get a time complexity of max of p multiplied by p, right? But that's only, we're getting this max p from the fact that we're having to iterate through every single value in this k range. But why should we iterate from 1 to the end of that k range? Why? In which case, in the worst case, we'll have to go through every single value. Why don't we instead apply binary search on this k range? What's that going to give us? Well, we can reduce max of p to the log of max p. So if we can improve this, this is what our time complexity is going to be. Okay, so I ran out of room, but this is the improved time complexity. Basically, we're taking this variable and applying a log to it, which is going to reduce it a little bit. So let me show you quickly how that binary solution is going to work. It's pretty straightforward, and then we're going to jump into the code. So we're going to be using binary search. We're giving given this input array and we want to eat every single pile in less than or equal to 8 hours. So we know that the potential rate that we're eating bananas at, K, is going to be between 1, that's the minimum it could possibly be. The max it could possibly be is going to be whatever the max in our input array is. We know the max value is 11. We can find that in linear time. So then we're going to initialize a range like this, right? This entire range that we have going all the way from 1 to that max value 11. So in other words, we're going to have a left pointer at the minimum and a right pointer at the maximum. Then we're going to compute the middle by taking the average of left and right. 1 plus 11 divided by 2 is going to be 6. So our middle is going to be here. In other words, our K that we're trying is going to be here. This is the rate that we're going to eat bananas at. So we're trying the rate of 6. Does this work? Can we eat all these bananas with a rate of 6 bananas per hour in less than or equal to 8 hours? Can we do that? Well, how many hours does the first pile take? Well, 3 bananas, right, divided by the rate, which is 6, is going to round up to 1. That means it took us 1 hour to eat the first pile. The second pile, 6 divided by 6, is also going to take 1 hour. So let's just count the number of hours. So the third pile, 7 divided by 6, is going to round up to 2. So that's going to take 2 hours. The third pile, 11 divided by 6, is going to also round up to 2. That means 2 hours. So we just did this in 6 hours, right? Is that good? Does that mean we found our solution? Well, 6 is less than or equal to 8. That means we were able to eat this entire thing in the time threshold with a rate of 6 bananas per hour. Is this our solution? Well, remember, we were looking for the minimum K value that allowed us to do this. So this might be the solution, but let's try all the smaller values, or let's start our binary search in this direction to see, is there a smaller value than 6 that we can use for our K value? So basically what I'm doing here is, if we're able to eat the entire pile in the threshold, what I'm going to do is then start searching in the left direction. So what I'm going to do is take my right pointer and shift it to K minus 1, because now we're searching this entire range. What if the opposite was true? What if I tried this K value, but I was only able to eat the entire banana pile in, let's say, H equals 10 hours? That means I went over the threshold, right? That means I went over the time. So what does that mean? Does that modify our binary search? Well, what that tells us is our rate of eating bananas, 6, was too small. We didn't have enough time to eat all the bananas in the given available time. So what we have to do is increase our rate of K, right? So in that case, what I would do is I would search the right portion of the range. So what I would do is take the left pointer and set it to K plus 1 over here at the 7. So that's how this binary search is going to be working. But so far, we do have one possible solution, and that's 6. So now our new right pointer is pointing over here, and our result is for now going to be 6. So once again, we're going to take the left and right, add them together, divide by 2. That's going to give us 1 plus 5 divided by 2 is 3. So our K is now going to be at this 3 value. So now let's check. Can we eat all the bananas in less than or equal to 8 hours? How many hours does the first take us? Well, we're eating at a rate of 3 bananas per hour. The first pile is 3. That's going to take us 1 hour to eat it. The second pile, 6 bananas divided by 3. That's going to take 2 hours. The third pile, 7 divided by 3, rounding up, is going to be 3 hours to eat that pile. Last pile, 11 divided by 3, rounded up, is going to be 4 hours. So when we total all of this up, it's going to give us, I think, 10 hours. So just like we discussed before, we went over our threshold. We took too long to eat these bananas. So what that tells us is this did not work. 3 bananas per hour doesn't work. Let's start searching to the right of our range. And remember, when we took this right pointer and shifted it, what we basically did was we said that none of these values are ever going to be considered again. We're now searching in the other range. That's how binary search works, remember? So since this did not work, we're not searching it, and we're not going to search any of the values to the left of it. So what we're going to do is take this left pointer, set it to K plus 1. So once again, we're going to take our pointers, add them together, divide by 2, and in this case, we'll just round down. So 9 divided by 2 is going to be 4. So I'm going to put my K value basically where left happens to be at 4. So let's see, with a rate of K equals 4, can we eat all the bananas in less than or equal to 8 hours? The first pile takes 1 hour, the second pile takes 2 hours, the third pile takes 2 hours, and the last pile takes 3 hours. So totaling all of this up, we get 8, right? So we were able to eat all the bananas in less than or equal to 8 hours if we had a rate of 4. So basically, let's compare that to our current result. So far, we found a value with 6. So really, we can update this 6 and say there's a smaller rate that we can use that happens to be 4. So now that we did find a potential result 4, let's see if we can find an even smaller one. Remember, that's what we did before. If we find a K that works, we're going to try to find an even smaller one. So what we're going to do is we're going to set our right pointer shifted over here. But notice how now the left and right pointers are not in the correct order, right? Left should always be to the left of the right pointer. That's basically how you know that our binary search has stopped. We don't have to continue the binary search anymore, right? And that makes sense because now we're searching values that we previously crossed out. We crossed these out, so how can we search them again? It makes no sense. So now we can stop the binary search and we can return the current result, which happens to be 4. 4 is the minimum rate of bananas that Coco could eat to eat all bananas in less than or equal to 8 hours. With that being said, let's jump into the code now. So just like I mentioned, we are going to have our left and right pointers initially set to 1. Left is going to be 1 and right is going to be the max that happens to exist in our piles input array. Now the result, we're not going to initialize it to 0 initially because remember we're looking for the minimum. So I'm just going to initialize it to R, which is the max in our piles, because we know at least this will work. This is the max that our solution could possibly be. And now we just start binary searching while our left and right pointers are in the correct order. We can compute the k by adding the left and right together and dividing by 2. And we want to count for this value k, for this rate k, how many hours does it take to eat all bananas? So let's initialize hours to 0 and go through every pile in the input array piles. So for any given pile p, we can divide it by k, which tells us how many hours it took. But remember, we have to round up. So there's a function in Python, math.ceiling, which will round this up for us. And whatever that happens to be is what we can add to our hours total. Once we've done that, then at the end of that loop, we're going to check if hours happens to be less than or equal to h, the given input. If it is, that means we can update our result to a new minimum, right? Take the minimum of the result, and whatever k happens to be, k is that rate that we're looking for. And if this is the case, then how are we going to update our binary search? Well, we're going to look for an even smaller k. So what we're going to do is set our right pointer equal to k minus 1. We're going to search the left portion now. If this wasn't true, how would we update our binary search in the opposite case? Then we would take our left pointer and set it to k plus 1, because that means the rate was too small, so we need to find an even bigger rate that will allow us to eat the bananas in the given time interval. And at the end of this loop, once the binary search has stopped, we know that we're going to be returning that result variable, which tells us what the minimum k happens to be. And believe it or not, that is the entire result. So I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve search a 2D matrix. And I really like this problem because it's not one of those problems that you need a fancy trick for. You can actually solve this problem just by using logic. So we are tasked with creating an efficient algorithm for searching for a single value in an m by n matrix. The matrix has two properties. In every single row, the integers are sorted from left to right, and the first integer of each row, for example, this 10, is always going to be greater than the last integer of the previous row. So greater than this one. So in other words, we know that each row is sorted, and then the next row is going to be greater than that. So technically, each value in total throughout the entire matrix is going to be in sorted order. So that's pretty good. In this example, we were given a target 3, so if we search for the target, we will find it right here. So then we can return true that it does exist. If it does not exist, then we simply return false. So how can we solve this problem? The key word here is create an efficient algorithm. What would be the brute force? Of course, we could do an algorithm O of m by n, basically by searching every single value in the input array, right? That's a pretty easy algorithm to do on a two-dimensional matrix, but can we do better? Of course we can, because they gave us a couple properties that this matrix has some sorting already applied to it. Assume that we just had a single row, like forget that we had a matrix. If we just had a single row like this one, and we know it's in sorted order, do you know an algorithm that can search for a target value in a sorted array? I know of one called binary search, right? And how efficient is binary search? Well, let's say the size of this array is n. We could do a binary search in log n time, right? But of course, we know that we actually have m different rows, right? So let's say we ran a binary search on every single row until we found the input target value, right? What would the time complexity be? Well, log n multiplied by m is going to give us a solution like that. So that's using the first property, knowing that each row's integers are sorted. And this is a pretty good solution, but can we do even better than this? I'll give you a hint. We're definitely going to have to use this second property that they told us. Each row itself is actually in sorted order, as in we know that the values in this row are going to be smaller than all of the values in this row, and all of the values in this row are going to be smaller than all of the values in this row. So can we use that property to, instead of searching through every one of these m rows, maybe we can actually do a binary search just to figure out which one of these rows to search in the first place? Because, for example, if we're looking for a target value 3, let's take a look at this row. This row could have any values between 10, which is the lower bound, and between 20. So obviously the target value 3 is not going to fall within that range between 10 and 20, right? So then the question is, okay, if the target value is definitely not in this row, we can cross this row out. But then which direction are we going to go? Are we going to look at the row above it, or are we going to look at the row below it? Of course we would want to look at the one above, right? Because above, the top row is going to have smaller values than the bottom row, right? So when we cross this row out, we can also say that, let's cross this row out too, because of course this row is going to have greater values. That's how the binary search is going to work, to even figure out which one of these m rows we're going to need to search, right? So we can reduce, instead of m, we can do a log m by running binary search. After we've ran that log m search, then we know, okay, this is the row that we have to do our second binary search on. So after we're done with that, we're going to do another binary search. So let's plus here log n, right? Log n for binary searching the row itself. So that's a better time complexity than we had previously, right? Log m plus log n. That's pretty dang good. So once we get to this row, we're going to say, okay, 3 is what we're looking for. Does that fall in the range between 1 and between 7? Of course it does. So either our target value exists in this row, or it doesn't exist at all. So let's run binary search here. So of course we're going to have 2 pointers, left pointer and right pointer. Then we're going to check the middle value. In this case, I think the middle value is going to end up being this one, because 0 plus 3 is going to become index 1. But let's just say it became this one, just to kind of show you what it's going to look like. Let's say our middle value is here. We're going to check, okay, 5, is that 3? Nope, 3 is less than 5. So what we can do in our binary search is cross out these values, cross out our pointers. Now our right pointer is going to be over here. And let's say we ran binary search again. We compute the mid to be over here. We check, is this 3? Nope, 3 is greater than this. So we cross this out and we shift our left pointer over here. Left and right are both here. Middle is going to be here as well. We're going to see, okay, either this has to be 3 or nothing, or 3 just doesn't exist. Of course, this is 3. So we found it. We can return true. And that's the entire solution. So it's just a double binary search, and we can implement that pretty easily once you kind of know how to do binary search. And if you don't, I'm going to show you how to do it right now. So now let's get into the code. So the first thing I like to do is actually get the dimensions of the matrix. So let's get the rows and the number of columns in this matrix. We can do that pretty easily because we know for sure that the matrix is always going to be non-empty. And now we're going to do the first binary search. We're going to look for the row that we need to find. So I'm going to have 2 pointers, one for the top row and one for the bottom row. Top row is 0. The bottom row is going to be the number of rows minus 1. So now we're just going to continue to do the binary search until we can either find the target row or we figure out that the target row does not even exist in the binary search. So one case is that the target value is even greater than the largest value in this row. So let's go to that row. Okay, first, before I do that, let me actually compute the row. So we want the middle row. In this case, we'll take the top and bottom and divide it by 2. That's kind of how binary search usually goes, right? So, and then we have that row. So in our matrix, we're going to look at that row and we're going to look at the rightmost value. In Python, you can do that with -1, but we could also just do number of rows minus, or the number of columns minus 1. But in Python, it's a little bit easier. So we're going to check, is this target value greater than the largest value in this row? If that's the case, what are we going to do? Well, then we need to look at rows with even larger values. So what we're going to say is our bottom row is going to end up being the current row plus 1, because now we want to look at rows that are larger than this row. Else, if the exact opposite happens, so let me copy and paste this, if the target value was even less than the leftmost value in the array, aka the target value was smaller than the smallest value in this row, in that case, we need to look at rows with smaller values. So we're going to shift our top pointer. Actually, I think I just did it backwards. So when we look for larger values, we actually want to take our top pointer and then shift it down, because when you go down in the matrix is when you actually get larger values. And if we want to look for smaller values, we're going to take our bottom pointer and then shift it up. In that case, we would want to set it to be row -1. So that's the case if the target value was either too big or too small. If neither of those evaluates to true, that means that the target value is actually does fall within this current row. In that case, we just want to break out of this while loop. And then we can do the second portion of the binary search. Now, it's possible that if we did not break out, maybe we just created an invalid condition where we figured out that the top and bottom pointers are invalid, right? Then our while loop would stop. And what that would tell us is that we crossed out every single row in the matrix and none of the rows contained the target value. In that case, we have to return false immediately. So basically, if not top is less than or equal to bottom, that means that none of the rows contain the target value, and then we can just immediately return false. If that's not the case, then we're going to move on to the second binary search portion, and we're going to run binary search on the current row that we found from the top and bottom pointers. So let me just copy and paste that. This is the row that we're going to run binary search on. And we're going to have a couple pointers left and right, which is going to be 0, and columns -1, because that's going to be the rightmost position in the row. And we're going to do pretty much the exact same thing that we just wrote above, a second binary search while left is less than or equal to right. Let's compute the middle point. We can do that by taking left plus right divided by 2, and now we'll do the same thing. So if we find that the target value is greater than the value in this target row at position middle, that means we have to search towards the right of the row. We have to search towards the right of this middle point, in which case we'll say our left pointer is going to be m plus 1. We're going to search towards the right. Else, if the exact opposite was true, then we want to search towards the right, so we can shift our right pointer to be mid -1. And else, the last case is if we actually did find the target value. In that case, of course, we can return true. Now, if this loop exited but we never returned to true, then outside of the loop, then we have to return false, meaning that we never found the target value. Okay, I just forgot that when we were copy and pasting, I forgot to change this condition. So the first one, of course, is if target is greater. The second else if is if target is smaller, then we want to shift the opposite pointer. And that is the entire code. So you can see that it's pretty efficient. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a very popular problem and probably one of my favorite problems of all time. It's jump game. So this is a very popular dynamic programming problem, but it can also be solved in a greedy way. I'm going to show you both solutions, and then we're going to code up the greedy solution, and it's very little code, so that's the good thing, but it's a pretty clever problem, so let's dive into it. So we're given an array of non-negative numbers, so all of them are going to be 0 or positive, and we're initially positioned at the first index of the array. So for example, in this input array, we're positioned at the first index, or the 0th index, right? The first position. So this is where we're going to start. We're going to start in this position. And so for every value in the array, for every element, the number itself, for example, number 2 in the first position, represents